Hey, welcome back to Fat Mama Physics. In this video, we're going to do lots of examples. That's right. We did example 3, 4, 5. This is what, 6 now? This is example 6, so I have to correct this on my sheet. Okay. I think I'm gonna do about 2 examples. We'll see how fast I go. Anyways, this is again talking about electric potential energy. Very fun stuff. So let's get started. How much work is done against the electric field produced by a 5 microcoulomb charge object when a 0.3 microcoulomb charge is moved a distance of 45 centimeters to 15 centimeters. So yes, we need to draw a diagram. I'm just changing these to mu's. They're actually not u's over there, okay? So drawing a diagram, we got a 5 microcoulomb charge over here. So this guy is positive, okay? And then we got another small positive charge, which we're going to move from a faraway distance, or not really far away. It's only 45 centimeters. We're going to move this guy closer, where it's going to be 15 centimeters away from this positive charge. So if you're thinking, well, yeah, if I'm going to move 2 charges closer together, it's going to take work. It's going to be harder to get them closer together. So I almost think of it as the work being done is going to be the difference between the 2 potential energy states of these 2 points. So we're going to get the electric potential energy state at point 1, and at point 2, the difference is going to be the amount of work being done. And the electric potential at 2 is going to be higher because it's going to be closer. The distance is going to be closer. So I'm going to take EP2 minus the electric potential at potential energy at 1. Okay, that's gross. Okay, and to calculate that, this is going to be K times my big charge times my small charge divided by my first distance, which is 40. No, it's actually 15 centimeters. So 0.15 centimeters minus K big Q small q divided by 45 centimeters, 0.45. Putting in all my values, so 8.99 times 10 to the power of 9. You know what? I can just simplify this as K big Q small q and then 1 over 0.15 over 1 over 0.45. Okay, so my Q values are 5 microcoulombs. I'm going to be less lazy here. And then the other one is 0.03 times 10 to the power of negative 6 coulombs. And my inverses, 1 over 0.15 minus 1 over 0.45. I get 0.005993 ... and we are going to round this to 2 sig figs, which gives us 0.0060 joules. Okay, and yes, it's up there as well. Okay, there we go. That is the amount of work that has to be done to bring these 2 charges together. And you know what? We have time. Let's do the next example, 7. A proton. Let's draw this one. A proton is released from released very close to center of a also positive charge, fixed charge. Okay. What is the speed of the proton when it is 0.5 meters from that charge? Okay, so let's draw a diagram. Let's draw that charge, some fixed charge, which I'll write as this, I'll label as big Q. How's that? Okay. The proton is released very close by. So this little proton was here, which is 2.0 times 10 to the power of negative 11 meters. So yeah, for this one, if there's just so many numbers and maybe very dense information, look at the units to help you out. So this proton, of course, is going to want to move away from this positive charge. It's going to gain kinetic energy. It's going to accelerate away. And after a certain amount of time, it's going to be over here, which is 0.5 meters away. Okay, so that's the new state. And we want to find what is the speed of this proton here. Okay, so what that means is the amount, so that's kind of like a conservation of energy, in which the amount of potential energy lost by the proton will get translated directly to, or converted into kinetic energy of the proton. So since the proton is released at this point, the proton starts off with 0 meters per second of speed. And it's going to gain speed all the way up to 0.5 meters away. Oh, whoops, sorry. That 0.5 is from there to there, okay? So, sorry, diagram is a bit elusive there. Although it is very quite similar since the this is a very small distance. So, change in potential energy, this change in the potential energy is going to be equal to the kinetic energy that my proton gains, and which is 1/2 NV squared, in which the initial kinetic energy is 0 since it starts off with 0 speed. And in fact, I almost talked about this as in terms of, whoa, what happened there? In terms of this being an absolute number for the change in potential energy. But if we want to be more exact, technically speaking, the change in potential energy should be equal to the negative change in kinetic energy according to conservation of energy, in which there's no, for an isolated system. So, in fact, if we have to write this out properly, this would be the final potential energy of our system, of our proton, which is going to be further away. The number is actually going to be smaller, minus the potential energy that is closer, the initial state, is going to be equal to the negative change in kinetic energy. So its final kinetic energy is actually going to be quite high, and subtracting 0, which is going to be the initial kinetic energy there. So in fact, we're going to get a negative kinetic energy final here. So there's this negative sign. So if what I could do here, I could just move it to the other side of the equation and make these ones negative instead. Or actually, I'm just going to transfer that to the other side. So when I actually solve for this, this is going to be EPI minus EP final equals to the final kinetic energy of my proton. Because if you think about it, the initial potential energy is going to be bigger than the final potential energy, which is going to be further away. And that's going to be equal to the positive 1/2 mv squared. So that's why I talked about the magnitude instead of talking about the actual signage. So as long as you understand the concept of losing and gaining energy in your system, then you can kind of ignore my explanation. But just to be more technically correct, technically speaking, for conservation of energy, change in potential energy equals negative change in kinetic energy. Or that is saying the loss in potential energy is equal to the gain in kinetic energy. And the loss and the gain are designated by the negatives and the positives there. Okay, sorry, that took a bit to go over. So if I wanted to write this out properly, this is KQ proton over the first distance, which is 2 times 10 to the power negative 11, minus the same thing, KQ times the charge of a proton over 0.5 meters, and this is going to be equal to 1/2 mv squared of the proton. So let's calculate. Oof, I'm running out of space here. Okay, I'm just gonna cram this down over here. Okay, and my Q, what's that Q? It's a very 6.4 times 10 to the power of negative 18 coulombs. And then this is going to be times my proton, which is an elementary charge of 1.6 times 10 to the power of negative 19. And really, I can just say this is KQQ and then 1 over the first distance minus 1 over the second distance. Okay, so I'm just going to do that right now. Really, it's just to save me space. 1 over 2 times 10 to the power of negative 11. There should be 0 there. Okay, minus 1 over 0.5. Okay, and that's going to give me 4.6 times 10 to the power of negative 16 joules. That's the change in the potential energy. So I'm going to equate that to the kinetic energy, which is 1/2 mv squared. So that my speed is going to be 2 times this 4.6 times 10 to the power of negative 16 divided by the mass of a proton. Remember the mass of the proton you can grab from your data booklet, and which is 1.673 times 10 to the power of negative 27 kilograms, I think. And I'm going to take the square root because speed is squared. I get 7.4 times 10 to the power of 5 meters per second. And this is going to be directed, and it's since the speed, I'm not going to care about the direction. But there we go, meters per second. Phew! Alright, those were the two problems. So again, this is working pretty much with conservation of energy. Potential energy gets converted to kinetic energy, and maybe vice versa. We'll find out. Okay, so notice the problems we did before were associated with the work being done to put charges in a system. But now, if we don't do that, or instead we're just changing, instead of the work term, we're changing that with a change in kinetic energy term. Okay, so we're still dealing with energy changes. Anyways, thank you for watching. And again, we're going to have 2 more problems coming up. I look forward to seeing you again. Fat Mama Physics signing out.